All right, thank you for joining us today. It's my pleasure to introduce Juan Carlos Diaz Velez. He came to the United States originally as part of his pursuit and in his career as a dancer. So he's a professionally trained dancer who, along the way, combined his interest in the arts with the interest in science, getting a bachelor's in physics at Boise State University and later a master's in computer science at Boise State University. With that set of skills, and we always like to let our students know, with a bachelor's and then his master's degree in computer science, a nice combination with physics, he started working for now the last 10 years at UW-Madison. That's my undergraduate alma mater, and where I've run into Juan Carlos in the past. He started working at UW-Madison as a scientific programmer in the IceCube group, which is a neutrino experiment at the South Pole, which he will describe in great detail. Along the way, he reached back and began a collaboration with a university near his original home in Guadalajara. So he is going to complete his PhD in physics at the University of Guadalajara at the beginning of 2017. So after these paths in his career, he's completing his PhD. But as I said, he's been working for 10 years on this particular project. So we have a lot of really good information on this. He's in the area, in fact, for a high-energy physics scientific programming meeting in the Bay Area, as we heard in our first talk. Where's Michael? We heard in our first talk of the semester about programming in high-energy physics settings. And apparently the programming for the Large Hadron Collider, our first talk, and for particle detections for particle detections at IceCube are very much related. So we're very fortunate that he could come up during this time and visit us up here. Let's please welcome Juan Carlos Diaz Velez.
Thank you, Dr. Severson. So today I'm going to talk to you a little bit about neutrinos and cosmic rays in the scope of the IceCube Neutrino Observatory at the South Pole. So IceCube has been labeled possibly the strangest detector because it consists of a cubic kilometer size volume of ice deep in the Antarctic ice, and over 5,000 light detectors buried between 1,500 and 2,500 meters below the surface. So this is a very deep glacier, 3,000 meters deep glacier at the South Pole. It was built primarily to detect neutrinos produced in galactic and extragalactic sources. And the idea is with these neutrinos, we'll learn about the most energetic and most violent objects in the universe, and basically do astronomy with neutrinos. So here's an aerial view of the site at the South Pole and the IceCube construction. So you actually see here a drill camp and a South Pole station. So this is basically where people live. There's some labs in there as well. So Dr. Severson was actually down there a number of years ago working at the South Pole Telescope, which is located about here, I think. And then you see all the equipment for drilling. So here's basically a map of Antarctica. So the South Pole is located right about there. This is the old dome, which has been since demolished. And IceCube is located about half a kilometer away from, it starts about half a kilometer away from the station at the South Pole. So this is a schematic depiction of IceCube. So it consists of 86 what we call strings. These are cables instrumented with optical modules between 1,500 meters and 2,500 meters below the surface. So you can see a little Eiffel Tower by comparison to the size of this detector, which is probably the one of the largest instruments ever built. So the IceCube collaboration is an international collaboration made up of a number of educational institutions and research institutions in the U.S. So I work for University of Wisconsin, but we also have a lot of partners in Europe, in Asia, and Australia and New Zealand as well. So today I'm gonna, so IceCube does a number of different analyses. Basically I'm mainly gonna talk about two of them here, cosmic rays and astrophysical neutrinos. But there's also a lot of particle physics done, so we study neutrino oscillations, dark matter, and also do gamma ray detection and even earth sciences, glaciology and such. So classical astronomy is basically looking at the electromagnetic spectrum, so looking at wavelengths of light starting from infrared all the way to X-rays and gamma rays. So gamma ray astronomy consists of really high energy photons of light particles, basically, that have extremely high energies. Cosmic rays, on the other hand, are protons and heavier nuclei with energies up to several joules. And these are the highest energies that have ever been detected in the universe. Neutrinos, which are also subatomic particles, are tightly connected to cosmic rays and their sources, but they're neutral in charge and therefore are not subject to deflection and magnetic fields. So the idea is we can do astronomy with these particles because they point back to their sources. To illustrate this, the benefit of doing multi-wavelength astronomy, we can look at the galactic plane in different wavelengths. So this is an image of the galactic plane in radio, the infrared, near infrared, optical, X-rays, and finally gamma rays. So the idea is that by looking at the universe with different particles, different wavelengths, you obtain different types of information about the processes that produce them. So neutrinos are one of the fundamental building blocks of atoms, so of nature. They're part of the Standard Model, so they're subatomic. And normally you're familiar with neutrons, protons, electrons. These are what our atoms, our everyday atoms, are made up of. However, in nuclear interactions, neutrons actually can turn into protons and through the process of beta decay. And while studying this process, physicists discovered that there was something missing. So basically, there was a violation of a conservation of momentum. And so, in order to solve this problem, this new particle was introduced by Wolfgang Pauli. So basically, he invented this particle. So he theorized that there was a new particle that was very light, or either massless or with very little mass, and that has no charge, since we already had conservation of charge and conservation of mass, at least to within the measurable precision. Then this particle had to be neutral and very light. These neutrinos also have a very small cross section to interact through the weak force, so they don't interact readily with matter, and it means that they're also very difficult to detect. So basically, he apologetically stated, "I have done a terrible thing. I postulated a particle that cannot be detected." So this is basically goes counter to the whole principle of theoretical physics is our theories should be testable, right? We shouldn't just come up with untestable theories. Fortunately, the neutrino was actually eventually detected by Rines and Cohen in 1956 in a nuclear reactor, just 3 years before Pauli's death. Neutrinos are produced wherever there are nuclear reactions. So, for example, the sun produces more than 50 trillion solar neutrinos that pass through your body every second. And since they rarely interact, they can travel through matter without being detected very easily. So the sources of neutrinos include the sun, as I mentioned. There's cosmogenic neutrinos that were produced at the Big Bang and have very low energies. There's supernovas produce neutrinos. In fact, the supernova 1987A was the first supernova that was actually detected through neutrino detection at the Kamiokande neutrino detector in Japan. There's a lot of neutrinos produced in the atmosphere when cosmic rays hit particles in the atmosphere and produce nuclear reactions. Our own body produces neutrinos, so there's a certain percentage of atoms in your body that are radioactive. So it's like potassium that can decay and produce neutrinos in the process. These are very low energy neutrinos, of course. And of course, we have nuclear reactors that produce neutrinos. And then our own Earth has a lot of nuclear decay that produces neutrinos. So the range of energies that are produced by neutrinos is shown here. So basically, you have these cosmological neutrinos, solar neutrinos at the keV range, energy range. Then you have terrestrial neutrinos from reactors, background from supernova. Then we have atmospheric neutrinos from cosmic rays, and then at most extreme energies, we have those produced at active galactic nuclei, presumably, and cosmogenic neutrinos. So why do we expect to see neutrinos from astrophysical sources? Well, we go back to cosmic rays. So this has been over 100 years ago that cosmic rays were first discovered. So shortly after radioactivity was discovered, in experiments trying to measure the radioactivity coming from Earth and to calibrate instruments, Victor Hess took his electroscope up in a balloon to measure the radiation coming from the Earth. So basically, he thought if you go high enough away from the Earth, you see the background of radioactivity decrease. And in fact, he did see a decrease as he went up. But then as he kept going further up, he saw that the level of radioactivity actually increased. And the higher you go up, the more radiation you detect. So basically, there's radiation coming from space. And so then the big question was, what is this radiation? What are these particles, these cosmic rays? Are they nuclei, electrons, photons? So this was basically one of the big questions. But then, and the name cosmic rays actually comes from Millikan's belief that there were gamma rays. But in the 1930s, it became clear that there were actually mainly energetic protons and heavier nuclei that were bombarding the Earth. So cosmic rays, as I mentioned before, are the highest energy particles detected on Earth. So they're protons and heavier nuclei, which continuously rain down on Earth from outer space. And a small fraction of them have energies several joules, which makes them the highest energy particles in the universe. But the big question is, where do they come from? And can we do astronomy with them? Let me introduce a little bit of, for those of you that are not familiar with the units of energy that we use. The electron volt is the typical unit of energy that we talk about in particle physics and particle astrophysics. Usually, in physics, you talk about joules. However, since we're talking about individual subatomic particles, these numbers, the unit, it doesn't lend itself very well for this topic. So we talk about electron volts, which is basically the energy the kinetic energy obtained by an electron, which is accelerated through a 1 volt potential difference. And it's about 1.6 times 10 to the minus 19 joules. These are basically the, so you might be familiar with some of this notation in terms of storage, and I have megabytes, petabytes, terabytes, so forth, right? So, one zeta electron volt corresponds to 10 to the 21 electron volts, which is about the energy that would be contained in a soccer ball kicked, except this soccer ball contains several moles of particles, and we're talking about all that energy concentrated in a single subatomic particle. So this is a huge amount of energy per particle. And the range of the spectrum of energies that we detect from cosmic rays spans, so this is in scientific notation, so it goes orders of magnitude from basically the earliest particle accelerators to the Tevatron, which was the first generation CERN and the Fermilab accelerators. In the LHC, which you probably have heard about, so this is Large Hadron Collider in Geneva, Switzerland, and the crosses into France. So basically, this is the highest energy that we have artificially accelerated particles to. But we managed to detect particles that are several orders of magnitude higher energy than that coming from space. And so the question is, what processes could accelerate particles to such energies? So some of the candidates are supernova remnants. So supernovas themselves can accelerate particles to such high energies. But there's a process theorized by Enrico Fermi called first order Fermi acceleration, which basically is analogous to if you have a ping pong match, and you bouncing a ping pong back and forth, and you bring the paddles closer and closer together. You start transferring some of the energy of the acceleration of those paddles as they're coming in to the ping pong ball and giving that ping pong ball more energy. So these particles basically are going back and forth across these turbulent magnetic fields in the shock front of the supernova remnant, and are gaining energy at each interval until they escape. And so they escape and produce this power spectrum that you saw. So a lot more escape at lower energies, but some of them manage to stay in this loop until they achieve extremely high energies. There's also another candidate is the star collapse that produces a black hole and produces a gamma ray burst. So basically, as this ultra relativistic jet accelerates and produces a shock front, it produces this same type of acceleration, and can accelerate particles to very high energies. Another candidate for the most energetic particles are these jets produced at the centers of active active galaxies, which are basically can outglow everything else in the universe. So they're very energetic sources where there's supermassive black holes that are engulfing a lot of high energy particles and producing these jets. And so these sources are basically, we speculate that at what we refer to as the knee, so there's a change in slope here that is commonly referred to as the knee. So in this region, these are these are the supernova remnants, and then at the most energetic energies, at the highest energies, we have the active galactic nuclei. So why not do astronomy with cosmic rays and find out where they come from? In order to do so, we would have to have cosmic rays point back to their sources, so we'd be able to detect where they come from. And the problem with cosmic rays is that they're charged, but at the highest energies, they should have sufficient energy to not be affected too much by magnetic fields in space. So there's a number of experiments all over the world looking at high energy cosmic rays. Pierre Rocher in Argentina. There's a HAWK gamma ray detector in Mexico, HIRES in Utah, and then there's a number in China and Russia, and of course there's IceCube at the South Pole, which also does cosmic ray physics. So the rates of particles that we detect at the different energies, of course, we mostly detect particles in the lower part of the spectrum. So energies at about 10 TeV is 10 tera electron volts is what IceCube is energy threshold is. So this is about 1 particle per square meter per second. Then over here at the knee, we detect about 1 particle per square meter per year. And then down at the ankle, the Pierre Rocher Observatory basically can detect 1 particle per square kilometer per year. So these are very rare events, but they require very large detectors that have to be built on Earth, because you can't launch a satellite of this magnitude. Not yet, anyway. So here's basically what a cosmic ray shower would look like as it strikes a particle in it. So you might have a proton or heavier nuclei that strikes some particle in the atmosphere, the upper atmosphere, and then produces a cascade of other particles, each with lower energy, and then the particles propagate. So the most energetic particles, primarily muons, travel in a straight path from the initial interaction. But yeah, you get this very high, very extensive shower, and so there's surface detection arrays, including on top of IceCube. There's something called IceTop, which is a surface array that detects cosmic rays by looking at the extensive showers. So. There have been some indications from Pierre Rocher that there is an anisotropy from cosmic rays at very highest energies, but there have been no sources identified yet for cosmic rays. It's possible that, of course, even at these high energies, the particles don't really point back to their sources. Especially if they're intergalactic, magnetic fields will scramble their directions. And of course, cosmic rays are not the only game in town. So we can use other sources, such other messengers like neutrinos to learn about these sources. And the thing is, we believe that the same processes that produce these cosmic rays also produce neutrinos. So this is a schematic of the particle interactions that happen. So when so this is basically what happens in our atmosphere, but it also happens near the source. So there's a lot of dust and radiation near the sources. So if this is, for example, supernova remnant, you produce all these protons, and it's analogous to what happens in an accelerator. You have a beam dump in a target, and this produces a shower of particles, including pions that then decay into muons and neutrinos. And then these neutrinos can just travel for basically forever before, depending on the energy, before interacting with anything. In fact, so like for example, at 10 TeV energy range, a neutrino can travel right through the Earth and see it as or not see it, basically as if it was not there. So it's transparent. So yeah, so basically these are the types of interactions that can be produced by these proton interactions. So you can have neutral pions, which produce gamma rays, and then these gamma rays can be detected by gamma ray observatories like the Hawk Observatory in Mexico, or through the channels of charged pions. You can have muons and anti-muons that produce neutrinos that can be detected by large neutrino detectors such as IceCube. So this is analogous to what happens in the LHC. So basically you have an accelerator, accelerates protons to very high energies, and then collides them into a target that produces this directional beam of particles, and then you have magnetic fields that can separate the particles and detect them. So the two channels that I mentioned, so proton can interact with photon and produce a neutron and a charged pion, or it can just then produce a cosmic ray plus a neutrino, or cosmic ray and a gamma. So as I mentioned, cosmic rays tend to be deflected by interstellar magnetic fields. So this is the Lorentz force, which you may be familiar with. So if you have a magnetic field, you have you have a force that's exerted perpendicular to the direction of of motion, of the velocity of the particle, and the direction of the magnetic field. And so so basically, if you have a magnetic field in this direction, and you have a particle that's traveling in this direction, it's going to be basically it's going to go into this loop and be captured by the magnetic field, at least the portion of the velocity that is perpendicular to the magnetic field. So Markov originally proposed the idea of a neutrino detector by installing detectors deep in a lake or in the sea and detect these particles to Cherenkov radiation. So this concept basically involves something which is sort of like the beta decay that I mentioned earlier, except instead of having a nuclear reaction that produces an electron and an antineutrino, in this case you actually have a neutrino interact with a proton or a neutron and produce a charged lepton, which is a muon. So a muon is essentially like it's one of the basic leptons, but it's very much like an electron, only a heavier mass. And because of its heavy mass, it can actually travel longer without interacting or being captured like an electron. So eventually it'll decay into electrons, but in the process it can produce a long track. So as this muon travels through a transparent medium, it produces Cherenkov light, and you can have photomultipliers that can capture this light. So Cherenkov light is basically, I won't go into detail about this, but it's basically when a charged particle travels through a dielectric medium, or anything in which it can travel faster than the speed of light is in that medium. So in fact, if there was a Lorentz violation, if particles could travel faster than the speed of light, you would see Cherenkov light from vacuum. But so in ice or water, if you have particles that are traveling very near the speed of light, the speed of light in the medium, in the water and the ice, are actually, it's much slower than the speed of light in a vacuum. So you can actually have this inequality be true, and what you have is something analogous to the shock wave to the supersonic boom produced by a jet when it travels faster than the speed of sound. So this Cherenkov radiation actually peaks at near ultraviolet and violet light, very close to the wavelength that our photomultipliers are sensitive to, and to ice basically in the blue. It peaks in the blue and the blue light range. And this is an actual picture of Cherenkov radiation. So this is a nuclear detector. It's submerged in water. And so what you're seeing is the light produced by electrons that are being accelerated as the product of nuclear decay, and they're traveling faster than the speed of light of water. So you actually see this glow from nuclear reactor. So to capture this light, you have this photomultiplier tube, which basically is sensitive to even one photon can produce a single photoelectron, and produce basically a drop in voltage or a current, basically that can be recorded and used as a signal. So the Antarctic ice is actually very transparent to this blue light. Can travel more than 200 meters, and we've actually studied the optical properties of the ice at the South Pole in detail. So this is a model of the scattering and absorption as a function of depth and wavelength. So there's actually a dust layer about halfway through IceCube that we have to take into account in our simulations and our algorithms that detect that reconstruct the tracks produced by muons. But other than that, it's actually very, very transparent. So
Carlos, can I ask about that?
Yes.
That map is showing how transparent, or it's the amount of scattering. So the higher it is, the scattering. And so you were pointing to something at about 2 kilometers down, where all of a sudden the scattering is much, much more at all wavelengths. So there's like a dusty layer in the ice.
So the belief is it's basically that there was a volcanic eruption about 100,000 years ago.
100,000?
Yeah.
I mean, that's the geology.
Yeah.
As you're trying to set up an experiment to do astronomy, you figure out something about geology. That's fascinating.
And basically it's completely opaque by all means, by our standards, and so it's a lot of times you basically in the reconstruction of tracks, it looks like 2 blobs, which I'll talk about the taus in a minute, but we have to distinguish that, take into account that you don't expect to see any light at those depths because of that. But I mean, we actually, one of the research papers we published was in a journal for glaciology, so we've done a lot of interdisciplinary research beyond astrophysics. Yeah, so this is again the schematic of IceCube. So we basically deployed those photomultiplier tubes that I mentioned, about 5,000 of them. They basically start. So this is all in part of the going back to the ice layers. So this is not frozen water that this ice is made of. This is snow that has accumulated over thousands and thousands of years, and just from the pressure that accumulates as more snow piles up, it just compresses, and so it's not a uniform volume of ice. In fact, the top part is not instrumented because the scattering is just scattering length is just too short, and it's impossible to do any detection at shallow depths. In fact, the very top is what's called firn, which is really compacted snow and is completely opaque. So this is basically what you expect this Cherenkov cone to be produced as a muon track goes through the ice. And then these blobs represent a detection by one of our modules. So the color is representative of the time. So red is earlier and blue is later. And so based on the timing and the size of the blob represents the amount of light detected by that particular instrument. And so this is how we illustrate our event viewer and how we reconstruct the track. So based on the timing and the amount of charge that was deposited, we can reconstruct the direction from which the muon came. Let's see. Okay. Well, so in order to build this detector, we basically had to, how do you drill holes in the ice and deploy these modules? We basically had to heat up water. And if you've ever held an ice cube under the faucet and just let hot water drip on it, and basically just drill a hole right through it. And that's basically the process that we use to build this detector. Of course, the system is a lot more complicated in that it has to maintain a certain flow and temperature, and so it has some complicated electronics to regulate all of this. But yeah, basically burned jet fuel, heated water, injected the water in the ice and built these holes. And then you have a short amount of time to deploy the sensors before the water freezes back up. So yeah, it's basically 200 gallons per minute with 7 megapascals at 90 degrees Celsius with a 4.8 megawatt heating plant that we have. So this is basically one of the housings where we this is the drill, the fern drill actually, which just melts through the top layer before we, and then this is the regular drill which just injects water. So this is, we basically have a little housing like a tent in which people can work, and so they're not exposed to the extremely low temperatures, even though it's summer. A typical summer day at the South Pole is worse than the typical winter day in Wisconsin, which is saying a lot. But we do have occasionally days in which the temperature is colder in Wisconsin than it is at the South Pole, and we like to brag about that. So this is the drilling, and then you have all the PMTs and housed and ready to deploy. And then you basically add them to the cable, connect them, and start lowering them down into the hole. And there goes one of the photomultipliers as it starts its journey down the rabbit hole. it's a little cartoon animation of how the whole system works. So you basically have the fern drill through the top layer just by melting the tightly packed snow. And then once you get to deep enough where you're in solid ice and you can just recycle the melted water, then you start just pumping hot water down, and the process takes about 48 hours per hole. And then you retrieve the hose. So this is a long hose that's on a reel connected to the I guess I thought I had the deployment there as well, but basically the same process, just deploying the string down. And then all these holes then have, of course, the cables have to go to the IceCube lab. So this is a building that just houses all the electronics for the data acquisition system for IceCube, including the southernmost computing cluster on Earth, which, believe it or not, has challenges in terms of cooling, because you can't just open the windows and let the computers cool to the ambient temperature, otherwise they won't work. But so you have to maintain the right temperature gradient. So this is our DOM, or digital optical module. So it's not just a PMT as I showed, but it actually includes some electronics. So there's an onboard computer which digitizes the signal and sends it as in digital form to the surface to be triggered. It also has a built-in trigger which communicates to nearby modules to make sure that it received a coincidence, because you actually have a lot of triggers, false triggers, that happen just from noise, from thermal noise. And actually, even at these temperatures where the thermal noise is very low, we actually get a different kind of noise, which is not Poissonian, that happens because there's impurities there's salts in the glass that actually decay and produce photons that then fluoresce in the glass, and so you have to account for all of this, and so you have just random noise hits, and you have to trigger next to modules next to it. Let's see. So this is basically what the DOM does. It takes a waveform produced by the current or voltage drop and the PMT, and converts it into digital bits. So this is basically the waveform on top of the digitized. So you see the points, which are the individual bins, and the digitizer. So this is timestamped with a precision of 2 nanoseconds, and sent up to a computing cluster at the surface, which does the reconstruction. So of course, IceCube was a very large endeavor, and it took several years to complete. So the first year we deployed a single string to actually this one to string 21, just basically to test the system and make sure that we could do this. Then after that, we deployed an additional 8 strings, and then we completed a 22 string array, and then so basically after several years, we were able to complete the array. And then there's also an infill array of denser strings, more densely instrumented, which is used to do more particle physics, neutrino physics, studying neutrino oscillations, which then can use the larger array as a veto for some of the cosmic rays. And yeah, so these are the various seasons.
Question?
Mm-hmm.
It seems obvious you can't repair these things. Do they last
Yeah.
for many years?
So every DOM undergoes extensive testing before it's deployed. But regardless, we do have some instruments that fail eventually. But actually the the rate at which they fail is actually pretty low. So we will never be able to retrieve these instruments. Once they're frozen in, they're there permanently until the glacier slides into the ocean. And,
The ones that are 12 years
Yeah.
old are still working.
yeah. So we expect this to keep working for another 10 years at least and beyond. So at least we're funded for the next 10 years. And but yeah, so I wanted to show you this quick video. So this is basically 10 millisecond recording of muons from cosmic rays that hit IceCube of various energy ranges and everything. And so so in 10 milliseconds, this is basically what the detector sees. And so you need to have very high precision triggers, very high resolution triggers and binnings for all the modules. And so you can break up each of these events into a separate event that happens in time. Of course, there are events that do happen to coincide within that time window, but that's on the order of like less than 10% of the events.
So each one of those streamlines sees a muon?
Yeah.
Okay, and this is only 10 milliseconds?
Yeah.
Okay.
So
How
we-
many neutrinos in that picture?
Well, we detect about 250 neutrinos per day
Okay.
and about 3,000 muons per second. So this is our signal to background ratio.
And the white streak is a cosmic ray.
This is a high energy muon bundle. So it's from a cosmic ray, and so you have a lot of these white spots are basically stochastic energy losses where they do pair production and different subparticles that are produced, Bremsstrahlung processes. Yeah, so these are our different rates. So atmospheric muons, we detect about 10 billion events per year. Atmospheric neutrinos, we detect 10 to the 5. And then cosmic or astrophysical neutrinos, we detect about 10 per year. The types of neutrinos that we detect, so these are the signatures that we're looking for. So there's a cascade. This is an electron neutrino, which basically produces a high energy electron as it interacts, and that high energy electron just disintegrates almost instantly into thousands of particles, pair production, and lower energy electrons, basically, and positrons, and so it basically produces this spherical cascade that has very poor angular resolution, because even though it is traveling at the speed of near the speed of light, this process happens really fast, and so the basically in order to reconstruct the direction that it came from, you're looking at the elongation. And given what I said about the properties of the ice, this is tricky. You have to really understand the scattering and absorption of your ice so that you can estimate the right timing for arrival of light into different sensors from an event like this. The muons have very good angular resolution, but actually have very poor energy resolution because they're not contained. So the cascades, if they're fully contained in the detector, then it's a calorimeter. So you basically can get a very good estimate of the energy deposited by these events. And with this one, you get a very good angular resolution, but poor energy resolution. And then the tau neutrino, which is the third type of charged lepton, which is similar to the electron and the muon, except even another order of magnitude higher in mass. It actually tends to basically produce interact and produce another tau in the ice. And so basically it's a combination of these two events. So you have a cascade produced similar to the electron, and then you have a track, and then it has a second interaction after that.
And the color code is for the precursor or the
It's the timing. So this is earlier and this is later. Yeah.
blue is later.
Yeah. So this is an animation of. This is a simulation of a track in the ice. So you're actually tracking all the individual photons as they scatter and propagate through the ice. We basically use GPUs for graphical processing units, basically video gaming cards for simulating all of these events. And yeah, so you can see you have all the blue light is the one that's scattered the most. It's out on the outer edges. And then you have similar cascade event. So you can actually see, it looks very spherical, but you do see some difference between one side and the other in terms of timing.
So you'd be entering from the left.
Yeah, exactly. Yeah, this is a real event. So this is one of around 300 TeV cosmic ray muon bundle. So very high energy muon produced by a cosmic ray, not by a neutrino. But yeah, so with all these detections, so I mentioned the very few number of events we detect. So there's one of the main things that we're looking for is we're looking for sources of these sources of neutrinos, right? So are there parts of the sky that produce more neutrinos than other parts? And so I didn't mention Amanda, but Amanda was the precursor to IceCube. It was a much smaller array located in this, right within the volume that now encompasses IceCube. In fact, the modules are still there, even though they're not doing anything. But so this was the first neutrino study done. It consisted of 17 events, and of course it gave very little information. Then later, with the completion of more strings of Amanda and more years of data taking, we were able to produce this map. So this is the northern hemisphere. One thing I didn't mention is that we're mainly, so IceCube is located at the southern tip of the Earth, and we're actually looking downward for our detection, right? Because as I mentioned, we have the high event rate coming from above, from all these cosmic ray muons, but these muons will interact and die out, decay, and they can't travel through the Earth, whereas a neutrino can travel right through the Earth and be detected when it interacts in IceCube. So one sure way of separating neutrinos from cosmic ray muons is to just do an angular cut and say, okay, anything that's coming from below is a neutrino. Anything from above, we have no idea, most likely a cosmic ray, so we won't even look at it. Of course, then we had IceCube. We did this similar analysis. IceCube has much higher rate, so we were able to produce denser sky maps. No statistical significance found anywhere in the sky. And then we figured out how to detect neutrinos from the southern hemisphere as well, which I'll talk about in a minute. But so, and not only that, but also separate neutrinos produced in the atmosphere by cosmic rays from neutrinos produced far away at the sources. And so this is a sky map, much smaller number of neutrinos than these, of course, but these are the astrophysical neutrinos that we know were produced not in our atmosphere, but beyond. You do see a little hot spot there, but it's not statistically significant. It's just, you basically, if you run random numbers and throw neutrinos into the sky, you get this about 20% of the time. These extremely high energy neutrinos that we detected. So this is a result that was actually published in Science magazine. So it actually, the way it came about was first in a high energy neutrino study, we ended up with two neutrinos. that really stuck out, and they actually were detected accidentally. They weren't supposed to be detected in that particular analysis because they were supposed to be. This analysis was looking only for things coming from the opposite hemisphere, but it actually found these because they were misreconstructed in terms of direction. But after having found these, we actually realized that by studying the topology of these events, we figured actually if you look at these events, you don't see the IceCube strings here, but there's nothing, these are completely contained. So you don't see, if these were produced by a cosmic ray that produced a neutrino, that cosmic ray would also be accompanied by charged particles. So in that shower that's produced in the atmosphere, you produce neutrinos, but you also produce muons. And so you would see some, at least one muon entering the picture here. So this gave us the idea of basically reducing the fiducial volume of IceCube and using the outer layers and even the dust layer as a veto region. And saying basically, if you see something here that doesn't appear to be accompanied by any charge deposit in the veto region, then you have an astrophysical neutrino, as long as they're coming from the southern hemisphere, because the ones coming from the northern hemisphere would not be accompanied by a charged lepton. So after we did this, we found 28 events, originally these two events that I mentioned were dubbed Ernie and Bert, after the Muppets from Sesame Street, because basically Bert is a little more elongated along the z-axis, and Bernie's a little more elongated about the x-y axis, in reference to the shapes of the puppets. So of course our grad students had fun naming the remaining neutrinos, and they were named after all sorts of Muppets from the Muppet Show. At this point, we've detected so many that we've given up naming them the neutrinos. But yeah, so of course this detection made the cover of Science magazine. It was named the biggest physics discovery of 2012, and so on the cover is Snuffleupagus as the neutrino depicted there, because it has a little bit of track. So here you do see a track, but this is a track. So if you look at the color coding, it actually starts. This detector starts in here and then exits through a track. So after doing statistical analysis of all the different neutrinos that were detected, including the ones from the northern hemisphere, basically just looking at the fluxes of neutrinos that you expect from background muons, from atmospheric neutrinos, and then including the uncertainties from different models. Then you basically end up with this excess. So of course this is a log scale. Of course these correspond to 1, so there's 1 in each of these. There is nothing detected in these energy bins, which doesn't mean that there's nothing there. It's just we didn't detect anything, so we just have upper limits for those. But this is the conclusive result, indicating that individually we can't say that each one of these neutrinos is from an astrophysical source, but just statistically we can say that the bulk of them are of astrophysical origin. And then this is the same plot. This is in terms of the actual energy. So this is the total light collected in the detector, and this is the actual energy translation between light collected and the actual energy of the track or cascade that was detected. And this lower end here has to do with the threshold of the veto analysis. And yeah, here's the sky map that I showed earlier. So these are the sources. So the x's correspond to muon tracks or muon neutrinos, and the pluses correspond to cascade events or electron neutrinos. And of course, the cascades have a much poorer energy angular resolution, so they're the reason why these overlap into this region here that seems to look statistically important, but it's not, is because of the poor angular resolution of the cascades. So, I mean, we're still actively working on getting better angular resolution for cascades, and also collecting more data will help resolve some of these questions. It is interesting that it is close to the galactic center, but I didn't say that. Other scientific results that we have published. So this is something that I've been involved in actively. Is cosmic ray anisotropy. So while most of my colleagues at IceCube like to throw away the cosmic rays that we detect, I actually am a scavenger, like to go through these cosmic rays and do an analysis with them. So we actually collect really high statistics, 10 billion cosmic rays per year. And then you study the arrival directions in terms of large-scale structures and see that there's a very small anisotropy on the order of 0.1%, where you see an excess of cosmic rays coming from one part of the sky versus the other. And then if you basically do a fit to a dipole and a quadrupole for this and subtract that, you are left with the residual anisotropy on the order of 0.01%, which has smaller features. And this has been reproduced for several years in a row, revealing the same features. It actually this analysis has been done with Northern Hemisphere detectors, and these features seem to be actually be coupled to what you measure. So this is Tibet, the Tibet array in China, in Tibet. That's politically incorrect, I guess. So in Tibet, but the Chinese run it, so it has detected the same anisotropy, and you see it's a continuation of the large-scale anisotropy at the South Pole. This is what IceTop sees. So actually at higher energies, IceCube and IceTop, which IceTop is sensitive to higher energies, you actually see a flipping of the dipole. So the minimum actually comes from the opposite side as the opposite, and it's not a smooth transition. So it actually you see. So this is the IceCube anisotropy, and then you see the IceTop anisotropy, and even the IceTop at higher the IceCube measurements at higher energies also reveal this flip, and it's very spontaneous. It doesn't happen continuously as you raise the energy threshold. So it's kind of interesting. So these should point, and of course there's a lot of speculation as to what the nature of this is. There's people speculate about the nearby sources for the dipole anyway, not the small scale structure, but and then attribute the small scale structure to magnetic features in our features in the magnetic field in the heliosphere. But even some of the large features are something can be attributed possibly to structures in the heliosphere. So beyond IceCube, so now that we're happy with the results from IceCube, of course, you run IceCube 1 year, you run IceCube another year, you double your statistics. You run it a third year, you don't double your statistics anymore. And as you increase the data taking, you get diminishing returns statistically. So the next thing is to go to a higher volume in order to detect enough high energy neutrinos to be statistically significant. And at the same time, we're looking at a smaller detector infill to do particle physics with. So I'll just go through my conclusions here. So basically, neutrinos are awesome. We're at the dawn of neutrino astronomy. And then the Antarctic ice is an excellent medium for detecting neutrinos. So I should mention there are other neutrino detectors. There's particularly in the Mediterranean, there's the Antares detector, which is similar to Amanda, the predecessor of IceCube. And under construction, currently there's a kilometer size detector, but it's not currently built yet. So that should complement the results from IceCube. But so yeah, we've detected the first astrophysical neutrinos, and then large detector volumes are needed, but even larger ones are needed to resolve point sources probably. In addition to studying to doing astrophysics, it's also an important instrument for particle physics and a variety of other scientific topics. And the next generation neutrino telescopes is underway. Finally, I just want to do a plug for WIPAC. So this is the Wisconsin IceCube Particle Astrophysics Center. So we actually, in addition to IceCube, we house a bunch of other experiments. So this is our main topic, but there's scientists working on these other topics, including this project, which is using cell phones, iPhones and Androids to detect cosmic rays. So you can actually install this app on your phone and participate in this. So basically, your camera can detect Cherenkov radiation from muons and electrons, and you can participate in an experiment. So there's an REU program, so research opportunity for research experience for undergraduates. So if you're interested, you should look it up and apply. So we have you basically. There's an application form at the UW Physics page. You just have to send your official transcripts, 2 academic references, and then write an essay explaining why you want to participate in an astrophysics program. And there's a number of topics. Of course, neutrino astrophysics is one, but we also have other projects at UW that are of interest. And the list goes on. I didn't include everything.
What's the deadline for applying for that?
It's in February, I believe. Yeah. Final thing. So of course, everybody that goes to the poll has to have a photo op at the poll. Everybody does something unique, and so this is kind of a cartoon, with the competition. It says you see a first upright piano pole to the South Pole, and then you see the grand piano there already. So, so my own, as Dr. Stevenson mentioned, I was a ballet dancer first, and so this is what I decided to do at the South Pole. So this is a South Pole marker. So I went through every time zone in a few seconds.
We're going to have a short period of time for questions. If some of you need to leave right now, please do so very quietly. I'd like to start the questions session right now.
And what's the IceCube Master Class?
Oh, so the IceCube Masterclass is actually something geared for high school students, so the different IceCube institutions participate in this, and they typically target it to their community. But we also have sometimes webinars basically for the IceCube Masterclass, and so there's information at wipac.wisc.edu. Where you can learn about all of these different things.
I was just interested in how you actually detect, the height of where there's a collision with a neutrino in the column itself, because it sounded like the detector was placed towards the bottom.
Right.
So scale where it hits.
Yeah. So let me bring up.
isn't it just a column of ice?
And those detectors all on the string.
Yeah.
Yeah, so of course, I mean, here you don't see the volume of ice above an event like this, but we're basically just, I mean, if something interacts in the part that's not instrumented of the ice, we'll detect the muon that comes out of it, but we won't be able to say much about it. So if it's downgoing, it's coming from the southern hemisphere, we can't distinguish it from a cosmic ray. If it's upgoing and it interacts above the detector, we won't see it at all. But yeah, so we're only sensitive to the part that's instrumented.
Another question? Yeah.
What's your spatial resolution in the plane of the Earth and also in the z-axis?
You want to repeat?
Yeah.
What's the
How far
spatial?
the wires
far
away from
apart?
each other?
Oh, sorry. Oh, okay. Yeah. So the DOMs are separated. In the z-axis, they're 60 meters apart, and about 200 meters string-to-string separation. Yeah.
So when a muon comes down or a particle goes up and you detect it, does it scatter off of the detector, or does it just scatter on its own and we detect the scattering?
Well, so the interaction. I mean, these are really high energy interactions. So they basically just continue in a straight path from where the interaction happens. So it eventually gets absorbed. I mean, it decays and gets absorbed. But so the interaction. So in this case, for example, the interaction happened somewhere up here, and except this is a cosmic ray. But if it were a neutrino, so the interaction happened up here, and then at these energies, the angular separation between the originating track and neutrino track and the muon is practically null. And so, I mean, as you get to lower energies, you get more scattering between the incident particle and the products. But yeah, basically all the momentum is transferred to the outgoing particle.
And you had a thing for neutron oscillation or the
Oh, yeah, the
muon
neutrino.
oscillation from solar.
Yeah, so we did.
The columns would change.
Yeah, so actually, I do have a slide, an extra slide on this. So we actually did publish some neutrino oscillation results. So basically, just looking at the different neutrinos in terms of the fraction of cascades and muon tracks. And then to this day, we have not been conclusively detected a tau from a tau neutrino. And so so we can't really say anything about what the ratio of electron neutrinos to tau neutrinos is. So basically, the assumption at this point is that we have zero tau neutrinos, and basically we have 1 to 0 ratio of neutrinos from muons and muon neutrinos and electron neutrinos. But
Let's think. I mean,
Oh,
I
sorry.
think we have to wrap up the use of
Okay.
the room, but I think if we go outside and people want to continue to ask questions, and somebody would join us for dinner where we can ask the speaker many questions. But let's thank him again.